So here's problem number 4 from the 2011 AP Calc AB exam, and this is Form B again, so the second version of the exam. And this is another non-calculator question, and they've given us the fact that f is going to be a differentiable function. The domain of it is all positive real numbers, and what we know is we know the derivative of f. So they've given us the derivative, and it's defined for x is greater than 0, so the same as the domain of f, all positive real numbers. What we're asked to do in part A is find the x-coordinate of the critical point of f, and then determine whether we have a relative max, relative min, or neither at this position. So a critical number would either be a place where the derivative is undefined or a place where the derivative is equal to 0. If you think about this derivative, it is undefined when x equals 0, but that's not in the domain of the function, so we don't really have to worry about that. So we really only need to worry about when this derivative equals 0, and setting the derivative equal to 0, like I have here, is going to give us the result. If we multiply each side by x cubed and then add x to the 0, we get x equals 4. So when x equals 4, we have a critical number, and it's a stationary point, a place where the derivative is 0. And then if we think about building a sign chart for our first derivative, my number line mimics the domain of the function, so I'm not including 0, and I have this one place where the sign of the derivative could potentially change at 4, my critical number. To the left of 4, if I pick a value like 2, 4 minus 2 over 2 cubed is definitely going to give me a positive value. And then if I pick a number like 10, 4 minus 10 gives me a negative over 10 cubed gives me a negative value for my derivative. So my function is increasing to the left of 4, decreasing to the right of 4, and since f of x increases to the left of 4, decreases to the right of 4, we know we have a local maximum or a relative maximum at x equals 4. If you just had this sign chart and then local maximum at 4 and didn't have this sentence kind of summarizing what you're thinking when you arrive at the conclusion that we have a local maximum at 4, unfortunately you won't likely be given credit for this justify your answer step within the directions. So if you have a sign chart you're using to help you figure out if you have a local max or a local min somewhere, just make sure you verbalize your thinking before you conclude. In part B, we want to know where our function is concave down. So concavity is determined by the second derivative, so I actually used the quotient rule to take this derivative. You could have used the product rule and the chain rule. Actually, it would have just been the product rule. You could have used that here. You might have had some uglier algebra toward the end of this, but if you use the quotient rule, it's not too bad. So I thought of my quotient as 4 minus x over x cubed. So I had the derivative of the top times the original bottom minus original top times the derivative of the bottom over the original denominator squared. And then if you simplify this, that'll give you a negative x cubed. This is a little tricky because I distributed my 3x squared in and I got a 12x squared, but then I distributed this negative into that and I had negative 12x squared. And then if I distribute my 3x squared into the minus x, I get negative 3x squared, but then distribute the negative 3x cubed, but then distribute this negative into that term and it becomes a positive. And then if you just combine these like terms, you end up with this as your derivative. I factored the numerator here, so I basically just did a GCF and I ended up with just a nice simple numerator. Now my second derivative could change signs across any values where it's first undefined or first equal to 0. So I did the same thing as before. This second derivative is undefined when x equals 0, but that's not in the domain of the function, so I don't really have to worry about that. This piece of the numerator is going to be equal to 0 when x is equal to 0. Don't really have to worry about that, again, not in the domain of the function. But this piece is going to be equal to 0 when x equals 6. And so in my sign chart for my second derivative, again, the number line is supposed to represent the domain of the function. The only place where the second derivative could change signs is at 6, the one place where it was equal to 0, and also within the domain of the function. And then I looked at a value to the left of 6, like 3. You know, this is always positive, this is always positive. 3 minus 6 is negative. So if I have a negative numerator divided by a positive in the denominator, I'm looking at a negative value for my derivative. And then if I pick a value like 10, This is always positive, this is always positive because of the even exponent, and then 10 minus 6 is also positive, so I end up with a positive sign for my second derivative there. This tells you that your function is concave down when the second derivative is negative, concave up when the second derivative is positive, and again, don't just say we're concave down here, say why. F of x is concave down on the interval from 0 to 6, since the second derivative is less than 0 on that interval. In part C of this, we are given the fact that f of 1 equals 2, and then we want to determine the function f. Now the approach that I took here was, I could have done this from a strictly antiderivative approach, but what I chose to do is I chose to treat it like a differential equation. So I re-represented f prime with dy dx, the derivative of y with respect to x, and then I also distributed my x to the negative third into this set of parentheses and got 4x to the negative third, and then x to the first times x to the negative third, multiply like bases, add those exponents, and you get an exponent of negative 2. I separated my variables, so I multiplied the right side by dx, that's how the dx ended up over here, and then there weren't any y's to move to the left, so I just had a dy on that side, and then I'm going to integrate each side. So I integrate the left, the integral of 1 with respect to y is going to give me y, and then if I integrate the right, I'm going to add 1 to this exponent, becomes a negative 2, and then I'm going to divide by the new exponent, and then I'm going to do the same with this term, so I'm subtracting it since the coefficient is going to stay the same, and then add 1 to that exponent and divide by the new exponent. That's the side you want to tack your plus c onto. Simplifying this a little bit, 4 divided by negative 2 gives me a negative 2. Move the x into the denominator and change the sign on its exponent, so this term becomes a negative 2 over x squared. The sign of this fraction is negative, and if I subtract the negative, I can change that to addition. And then if I move this x into the denominator and change the sign on the exponent, I just get a 1 over x to the first. So this is my general solution to the differential equation. I want to use this condition when x is 1, y is 2 to figure out what my constant c is. So I put 2 in for y, 1 in for my x's, and then simplifying that is going to give you a constant of integration that turns out to be equal to 3. And so the function f that has this derivative and has this point on its graph is going to be given by this function. And it's just the general solution rewritten with the constant that we found in place of c.